Hi, everybody. Welcome to this talk. Thanks for the invitation. So today I'm going to talk about one aspect of my research, which is decentralization in optimization and machine learning. And so the nature of this talk will be, a little maybe more theoretical, but I'll try to explain everything. The first thing I want to mention is my research area is quite wide. Technically speaking, I'm at UCLA, I'm within the systems and control. This is core of my areas. But the talk that I'm going to be focusing on today is called distributed optimization, which sits within the scope of optimization, which is again another core of areas that I work in. Basically in the intersections of optimization and machine learning. But there are other areas that I actively work on, specifically network systems, some topics in game theory and stochastic processes, etc. But the topic today is basically main focus is on optimization. And I'm not going to assume much about you knowing anything about optimization. I'll try to walk you through the talk. So why interest in this area? So this topic, the talk will be about, part of it will be about network systems. And by the way, anytime you have a question, just interrupt me, okay? And by network systems, I mean basically a group of individuals, okay, that they can sense their immediate environment, they can communicate with each other, they can process the information they gather, and they can take actions, okay? And why are we interested to use basically these groups of individuals for tasks? Well, it's because they inherit robustness. If I happen to lose a few of these, my system at large still will be performing. They have adaptive behavior and they enable us to do tasks that are beyond individual capabilities. Okay, so that's the reason for interest in network systems. What are the examples of network systems? In sciences, you see network systems everywhere. For instance, flocking of birds, or in basically gene regulatory networks or social networks, right? These are good examples of right, like very large groups that they basically share information like opinion dynamics, right, etc., etc. So these are examples that we see in sciences, but also in engineering. There are many man-made systems that are network systems. For instance, when we think about traffic networks, this is something that so happens to be a network system in that individual drivers, they make decisions just based on what they observe locally, but then we have global phenomena that come out of individual decisions. And things like power systems, we actually do design them in a decentralized fashion because they can be much more efficient and easier to basically coordinate. And similar examples in water networks or in robotic examples, right? Collaborative, basically robotic systems like the Amazon robotic warehouse that I've put here, right? So what I start to talk with saying that these network systems are sort of everywhere, right? And the last part example that I want to give is basically examples from machine learning, where now we're dealing with very large data sets typically, right? And basically processing this massive amount of data centrally can be really difficult and not efficient. And so one of the very interesting active areas in this area, in basically in machine learning, is collaborative machine learning. For instance, Google now uses a set of algorithms called, they're coined as federated learning in its Gboard on Android, where basically individuals, right, when you basically send your feedback in a private manner back to the central unit at, let's say in Google, there is a process of basically doing some weighted averaging to see basically gather information from basically individual clicks that people do. So this is quite interesting. I don't want to go to details of it, but collaborative machine learning is another example that that you could consider when we go through this talk. Okay. Now, what I want to talk about more specifically, now we want to be a little more specific, is the topic of today will be about a set of these problems that I just showed you. Many of them can be cast as optimization problems, right? As you probably know, many problems in machine learning are about optimization, right? You want to fit a bunch of data. This you can cast it as an optimization problem, etc., right? So the particular problem here is that we have a group of, let's say, agents. We call them agents or nodes or individuals, whatever you want to call them. And this group of agents, they have a private objective function, which I called it Fi. Okay, so this is a private objective function that individuals they have. They want through local interactions, they want to interact with each other, and they want to minimize or maximize, if you wish, the sum of these functions. So no one knows the sum, okay? No one knows what the sum is, but everybody, right, has access to one unit of it. This collaborative machine learning scenarios that I mentioned is an example of this, okay? And the difficulty is there's a common state, right? This common state X, right? Which the minimizer, we want to find that X, but again, no one has access to all the functions, okay? So this is the setup of the problem. It's important to understand, right? Before we move on. Now, I want to flesh it out a little more, right? And so the first thing to notice is if, let's say, the group of us who are in this talk, right? If each one of us has a local function that's private, okay? And we do not communicate with each other, there is no way that we can minimize the sum of the functions because we don't know. I don't know what function you have, right? So then at the minimum, we need a layer of communication so that we can sort of exchange our decisions, okay? Know about decisions, at least locally, of people who are in our neighborhood. So what do I mean by that? I mean that we need a communication network, okay? So that's the first thing we need. And I've tried to depict it here in this picture, okay? So this is the picture, right? So each individual has a function. Let's call it this F1, for instance. This is one of these functions, right? And individuals, they can exchange, okay, their decision variables, let's say X, with some neighbors, either out neighbors or in neighbors, however you want to think about it. So for instance, this node 1 may send message to node 6 and node 2, okay? You can communicate with these guys, okay? And so what's the goal? As I said, the goal is to minimize the sum of these functions, okay? And the state of the whole network, I call it with bold X, okay? So, and each individual, each one of us may sort of have an estimate of what the solution to this problem that I started with is, okay? And we can exchange our decisions with each other, as I mentioned. Very good. Now let's make this a little more concrete, okay? So what happens is, because, as I mentioned, because we have different estimates of what the solution is, a way to think about this problem, the previous problem that I just wrote, is because the previous problem that I wrote was that we want to minimize this function. And as I said, this X was a common state. This is a common state here, okay? This is a common state. I think you can agree with me that an equivalent way of writing this problem is as follows, right? To minimize this function where each of us is substituting our individual estimates of what the minimizer is, but we subject it to the fact that all these x's are the same. This is the same thing, right? So if we could agree, right, on the x, and basically we would be minimizing this function, which lives in a larger space, then the solution of these two problems, this problem and this problem, would be the same. This is the core idea behind collaborative, basically, optimization problems. So just as a summary, even if you want to put the math aside, is as follows. We make individual decisions, okay? But we exchange information and we try to agree, maybe by some, averaging of some sort, you may say, of what the solutions should be, okay? So this is the core idea of these optimization problems, okay? Now, in order for me to flesh this out a little more, right, I need to tell you a few little items about basically basics of graphs. If it's too basic, I apologize, but I want to set the stage right. So this communication network that I'm talking about is literally a graph, right? And by a graph, I mean a collection of nodes and arrows between them. And they call these directed graphs because communication sometimes is a one-way channel, right? And as I mentioned, I have a group of basically nodes, right? And there are these edges between them that are the way they communicate with each other, okay? Another way to encode a graph is by associating to it, okay, a matrix, let's say A here, right, which tells you which node can communicate to what, right? For instance, here, node 1 can communicate to node 2, right? This, right? Actually, node 1 has what's called a self loop, so it can communicate to itself. It can communicate to node 2. It can communicate to node 3. No, actually, it cannot, right? There's no edge going between 1 to 3, so we put a 0 here. And it can communicate to it cannot do to 4, but it can do to 5, right? So wherever there is, this is what this is saying. It's saying you can encode a graph in a matrix, right, with a pattern of zeros. These zeros, they tell you who you cannot communicate with, okay? Good. Now, and there is a notion of degree, okay, of a node, which means how many nodes are incoming or outgoing to a node, okay? There's another notion that's important in graphs, which is the notion of connectedness. Because if we want to, in a collaborative way, let's say minimize something, but we can never talk to each other. Suppose one of us is isolated somewhere. There is no way that we can have access to this function, right? To that node's function. So we also need basically some connectedness, and this is what's called strongly connected, meaning there is a path between any two vertex that you pick, right? For instance, if I don't know, if this is not, so if you pick this node and this node, I have a path going from one to the other, okay? And this should exist for all of them, so that I call it the strongly connected. The last notion that I need is notion of balancedness. Okay, this happens to be important. And a graph is called balanced if the number of incoming, okay, and outgoings to every single vertex is the same, okay, is the same. You can check if this graph right here is balanced or not, for instance. Good, so this is all I need from graph theory, okay? The way I represent basically my communication layer. Now, if you remember, I mentioned that what we like to have for our optimization algorithm is for us to basically be able to reach to an agreement, like a consensus, what we call a consensus. And so this is a very classical problem, okay? And even let's say the group of us here, we can play this game, right? We could be basically these nodes, right? And suppose each one of us has some opinion, right? Or some value, right? Let's say xi, okay? Each one of us has some value. And suppose that through exchanging information, okay, by exchanging values with our neighbors, suppose that we want to find the average, okay, of these xi's, of these initial values, okay? And as I said, the idea is the group of us can exchange information through a graph, which could potentially change with time. Let's say in the first time instance, maybe the graph looks like this, and in the second time instance, it might look like this. And at every time, we have our initial value, guys, and we send it to our neighbors. And as we receive the values, we average, okay? We average, we take, let's say number 3, 4, 5 comes from our neighbors, and we average it, and we set that as our new value, okay? And I'm claiming that if you do this process, of basically receiving information from your neighbors and you average, as you can think about it, the information kind of gets mixed between everybody, and we can reach basically a consensus, an agreement. This is one of the most basic, basically algorithms that you can think of, right? Is you have, as I said, some initial opinions as different nodes, and your objective is to find an algorithm that over time makes the value of everybody the same. This algorithm is very simple. Receive the value of your neighbors and average them and set them as your new value, okay? And I've laid it down here, right? As I said, you receive the state of your neighbors at each time and average it and then update your value, okay? I'm starting with something very simple. I started from, let's try to optimize collaboratively. And now I'm starting with a simpler problem saying, let's find, let's agree on something, right? Through exchange of information. And so this dynamics, you can write it in, if you think about it a little bit and sit down and write it down mathematically, you realize that it actually has a form like this, okay? Because you can write it as actually a product with a matrix, okay? So you take your state values and you do a product of it with a matrix that's called a row stochastic matrix, doesn't matter. But this dynamics, you can show that it actually does converge if your graph has enough connectedness, okay? I don't want to get to the details of this, but the first sort of point that we've reached so far is we can, through exchange of information, we can basically reach at least an agreement. Now, can we bump this up to optimize something? And so the idea of decentralized optimization, okay? Remember, the problem we want to solve is we want to solve this, right? We want to minimize this function. So one of the earliest work in this area came up with a very simple idea, right? This goes back to John Teseklik at MIT. And he had this very interesting idea. He said, look, this portion, guys, is consensus. It looks, the way it's written, it might look a little too complicated, but it's not. These are your neighbors. Okay. You take their values, which are right here. And this process is just averaging. Don't worry about it too much. These are the weights of that adjacency, and this is the number of neighbors. So when you take the weight and divide it by the number of neighbors, it's as if you're doing averaging. This is exactly average. So he came up with this idea that if I want to optimize this function and each agent I only knows his own Fi, what if I do a little bit of averaging with my neighbors, and in the other portion, I take a little step into the gradient direction. Okay, I hope that you're familiar with the basic idea that if you want to optimize a function that's nice and convex, you move in the, basically this is a descent kind of direction, right? You go in the negative of, this is, if you didn't care about your neighbors, this is how you would optimize fi. This is how you would optimize fi, right? But the idea of the first algorithm in this area in 1986 was, what if we do a little bit of averaging and a little bit of step in the direction of the gradient? And maybe if we balance this right, how much we listen to our neighbors and how much we greedily take our own private function, maybe this will work, okay? And it turns out that this actually does work, okay? This does work quite nicely, but it has a major issue. And the major issue of this algorithm is, if, remember I told you about balancedness, that the out neighbor, in neighbor has to be the same. It turns out if it's not, this simple idea of let's do a little averaging and a little bit of gradient, it will not work. And this actually took a long time. A step between this paper in 1986 until the time that issue of balancedness was pointed out. It took decades, but doesn't matter. The core that I want you to keep in mind right now is, for collaborative optimization, we do a little bit of averaging, okay, and a little bit of basically a step into the direction of our private function. Okay, good. Now that I got to this point, I hope sort of I told you at least about what the problem with true optimization is. Now I want to tell you a little bit about how we can update these dynamics, okay, the simple dynamics or algorithm to deal with this major issue in here. Because in real life, right, if you think about a communication sort of channel, right, it is noisy, it's uncertain, messages definitely only go in one direction, nothing is symmetric, right? So we can't make these assumptions and say, oh, this is the algorithm, and we go with it, okay? Now, one way to get around this is what's called average consensus. So I told you what consensus is, meaning we have a bunch of states and we want to agree on something. We don't care what that something is. But in the problem of average consensus, okay, we have a little bit of a harder problem. Remember, we were sort of sitting in this network, right? And basically each of us had an initial value xi0, okay? In the average consensus problem, we want to agree, but we want to only, the point we want to agree on the average of the initial values. This turns out to be a harder problem, okay, than just agreeing. Because the problem of consensus, agreeing, tells you that you want all these states to be the same, but it doesn't tell you what the value of it should be. In the average consensus is, by only exchanging information, we want to find the average of the initial values, okay? And I want to show you that these are not the same. So, now finally we're doing some examples so that you see what I'm talking about. This is what I was saying. So we have, let's say, 4 nodes here, and these are the initial values, 2, 4, 18, and 8. And you can easily, quickly check that the average of the initial values is 8. Now, here is what I'm going to do, guys. I am going to basically run a simulation on this graph where agents, they exchange the values. So these values, they send them to their neighbors. The neighbor receives these and averages them, okay, and puts it at its own value. For instance, this is at time 0, my algorithm. In the next time, my agents received the information and they updated their values just by averaging. And then in the next stage, they received information from the neighbors again, and they updated the values, and again, and again. And you can see after 25 times, they arrived at this value. But this value is not the average initial value. Okay? And this turns out to be a problem. And the reason that this happens, in fact, is that, for instance, if you look at this node 3, this node 3 is not a balanced node. It has 2 incoming, actually, in fact, 3 incoming with itself, but it only has this one as outgoing. Okay? So this is not balanced. So when this is a sort of an interesting exercise, is that you can quickly see that if your network is not balanced, when you run this simple idea of exchange information and average it, you're not going to arrive at average of initial condition. And that turns out to be a problem for optimization. I don't have the time to tell you why, but that's the case. Okay? I hope this a small simulation sort of told you the difference between just agree. These guys have agreed, right? They have agreed on 8.154, but they have not agreed, they have not found the average of the initial values. Now, the idea is, one question is, can you modify this algorithm of exchange information and average it so that you arrive at 8, you find this value? It turns out with a little bit of extra information, you can. And so here is another basically run of the same problem, okay? This time, I take the first setup that we had, okay? And I create an auxiliary version of it where I initiate everybody at 1, okay? And the way I do the updates this time is that I take this xi and I divide it by the omega I, okay? So I run the averaging sort of twice, one time on this and one time on this. And the values I receive, I divide them, okay? It turns out the averaging I do is a little different and the weights of the averaging is different. So when I show you the simulation, you're gonna see different numbers, but don't worry about that. These are the details that I don't want to get to. But at any rate, I am running some form of averaging in here. This is a weighted averaging, that's why the numbers are different. And I'm running the same averaging in here, i.e., each node receives the values from neighbors and computes the average and sets it at its new value. And I basically keep doing this update, right? This is at time 2. And every time I do a division in here. This division, what it really does, guys, is that it's going to get basically sort out the imbalanceless. These numbers tells you something about how imbalanced every node is. Does it have more basically outgoing, or does it have more income? Okay. And it turns out if you keep doing this, okay, these values down here, they actually do converge to the 8 that you were looking for. I have not made a proof here, but this is a statement that's true, okay? That there is a way, this algorithm is known now as push algorithm or push sum algorithm. Goes back to Kempe and in 2003, and it's a very nice algorithm that allows you to find the average basically of the initial values, even on graphs that are or communication basically channels that are but that are imbalanced. Okay, of course I did not show you the details of it. I'll write it down in a few seconds. Okay, good. Now we get to basically the second part of the distributed optimization. So remember, the first part was the idea was very simple, even though I didn't show any result or any basically statement, was that do a little bit of basically averaging and a little bit of move in the direction of or negative of the direction of the gradient of your own local function. Now, the only difference here is rather than doing the averaging that I showed you before, I am going to use this so-called push sum averaging, right? Where, as you saw here, I was running an extra auxiliary variable, omega I, and rather than basically using the average of the x's, I was using this variable y, which basically cuts out those imbalances, okay? So the algorithm is going to look a little more complicated when I write it down, okay? But core of it is what I just mentioned, okay? The variables also, I renamed them a little differently here. So if you remember, I was saying that the type of averaging I'm doing, because you saw different numbers. The first time I ran the simulation, right? The numbers look different than the second time because the averaging I'm doing is on a weighted version of X, okay? So this one is doing basically averaging number 1, and this is doing averaging number 2. So every node is carrying 2 variables. One is this SI and one is this omega I. They keep updating it for me, okay? And the Y, as you saw, is the division of these two, okay? And the Y is what's used to compute, basically the gradient is evaluated there. And then at every time I get a new X, okay? And I feed it back here when I update the algorithm again. But at the core, this algorithm, this whole portion of it is the push sum that we just saw, okay? Push sum averaging. And the other part of it is basically some gradient flow. So the idea is really the same. By the way, this alpha, I have not told you what it is, but in a few slides, I tell you how to select this. If you've had a course in optimization, you know anything about optimization, it's called the learning rate. And we typically set it in the right way for the optimization algorithm sort of to perform right. We don't want it to go to 0 too fast, right? But we want it to go to 0 so that at some point our algorithm stops updating in the direction of the gradients. I am not familiar at all with your background, so but if you do not know what I'm talking about, you can just ask. Now, one of the very interesting feature of the algorithm I've written here is that down here and here, I have sort of made an assumption that my graphs, they change with time. So my graphs, they change with time or can change with time, which is quite interesting, right? Because you are sitting in a real scenario, right? Where your neighborings might change. Many of the applications I talked about at the beginning of the talk, for instance, in the social network setting, right? The friends you're communicating with at every different time might change, right? This time you're talking with these 4 people, and next time you're talking with another 5 people, right? And however, this algorithm I've written here, it still has performance guarantees in spite of this, which is quite interesting. So what do I mean by that? Because remember, I told you that we need some connectedness, right? For instance, scenarios like this communication graph, right? These 2 guys, they can speak, they're not speaking with anybody, right? This one and this one. So if I were to only use this graph, right, it would not be possible because part of the function, let's say F1 and F2, that only these ones have access to, the rest would never see. But what if I have this scenario that at time 1, I'm using this graph, but at time 2, I'm using a different one. At time 3, I'm using a different one, and so on and so forth. And what if I compute the union of these graphs? So the union of these graphs is connected at every b time. Or better said, the union of these graphs at every b time is a strongly connected. So this is, let's say, b times step, right? So I union all these graphs, right? Do you remember when I say union, right? Meaning I put the edges together, right? For instance, I don't know, the union of these two graphs, when you look at it, if these are my nodes, right? The union graph will have basically this vertex and this vertex. Every vertex from basically all the vertices that I see from both graphs, I put them together. That's what I call a union graph. Okay, so it's a union of these two, right? And then I do union of all of them, right? So it turns out this B connectedness, being connected at every B times, is actually enough. You don't need to be connected at every time. What does it mean is that if you eventually get information from other people, even if it's not at every time instance, it's enough. And that's how our intuition says so too, right? And so here is a result that I want to display, okay? This goes back to 2015. As I said, there's a huge gap between early results in this one. Is that if you have this notion of B connectedness, okay, and your functions are nice, we usually talk about convex functions when we talk about algorithms. And as I said, if your learning net is set right, these are technical things I don't wish to talk about, then these estimates of yours are going to find the optimizer. This is the optimizer of this. This is really interesting in that no node has access to all private functions, but collaboratively, they are arriving at the optimizer and they're arriving in time with this rate, okay? As you can see, I mean, this is logarithm of t divided by square root of t. As t goes to infinity, this goes to 0, okay? And these are some coefficients that depend on the structure of your graph, how it looks like, okay? This is the part of it that is quite technical, and you can get some estimates of how this data looks like, okay? As you can see, I mean, at least quickly, they look pretty ugly as functions of nodes, okay? And this is a major open problem in this area, actually. And I'll have a slide explaining why. So what's the core of what I'm trying to say here? What the core of what I'm trying to say is, you know, this idea of optimizing some of bunch of functions, okay, without having access to all these functions centrally is possible, right? This rate is not the best rate available. There are better rates out there. This result is by now quite outdated, but I want to highlight a few points about such results, right? Basically, this dependency, because why do we do decentralization? We do decentralization because, at least in the context of machine learning, because we want to gain something from it. We want to reduce, right? Let's say the number of computations we do, or in a way, not have to use super duper computers, because we do process the information locally at small units and only exchange information. So it's very important to know how these rates change with number of nodes. For instance, if they scale very badly with number of nodes, if you give me an algorithm that works for 100 nodes, but it's not good for 1,000,000 nodes, this is not an algorithm that's useful in machine learning disciplines. And so the idea of improving these rates with respect to number of nodes has been quite important. specific, this is a paper in Journal of Machine Learning Research 2020 that, for instance, they showed in this paper that basically the distributed algorithms, okay, even though you do not have access to all the functions, they pretty much perform as good as centralized algorithms, okay? They obtain rates whose leading term, okay, is scaled very nicely with the number of nodes. The previous rate I showed you, it didn't scale so nicely, but this one does scale very nicely. These are higher order terms in T that are not important. If you don't know much about convergence rate of optimization algorithms, you will not know what I'm talking about. But what I want to say, at least highlight, is that results such as this has made basically decentralization optimization quite important in context of machine learning, okay? And the final note I want to mention is that real life situations are much more complicated because we also have element of randomness to deal with, in that, you know, the message that you send me may or may not arrive with some probability, okay? And so one of the, you know, advances in this area, if you get interested in this area, is to deal with these randomness issues. And it turns out that, for reasons that it's hard for me to explain here, is that it's hard to extend anything that I've mentioned in this talk in random settings. I mean, you can extend them to random settings, but things become more and more technical when we go to random settings. Nevertheless, the key behind extending these is actually goes back to basically updating that push sum algorithm. Because the push sum algorithm that we had, it turns out that you can update it in a way to deal with basically randomness by changing basically when to update information, okay? Again, it's a little technical. In case you haven't had a course in probability, this might be difficult to see, but this is the result I want to end with, saying that even if you are basically the union of your graphs, remember, right, is strongly connected in some probabilistic sense, okay? Even if it's connected in some probabilistic sense. So your graphs are drawn at random from a collection of graphs, right? But with basically, with high probability, let's say your graph is strongly connected, then you can obtain the same form of rates that I mentioned, okay? And show in expectation, your algorithm is going to converge to the optimized, okay? So basically the last part is everything that I said, there is a way of extending it to setting that are random, okay? There are tons of open areas, open problems in this area. Issues going from basically the scaling with the size of network is the biggest sort of active area of research in this area, I would say. And robustness, right? What if one of the nodes doesn't perform right? What if one of the nodes is actually adversarial and is sending information that is incorrect? Can my algorithm be updated in a way to deal with that? And of course, in these scenarios, there's going to be interplay between robustness and optimality, right? As I mentioned, decentralization in the context of machine learning is growing. You can think about decentralization in settings that are combinatorial, because the problems I talked about here are continuous optimization, but you can also look at them in combinatorial settings. So I think with this, I finish. Here's a bunch of references of my own work, but if there's any question, I'm happy to answer. I think I actually stop right here. Go ahead, guys. Can you, okay, let's see if I just see the questions that were asked in the chat. So somebody should maybe read it for, yes, this was just great. In this, I'm just going down the list. So let's see, I have what averaging of initial value, which I may miss. How we know that X1 we found that achieved the minimum? So I didn't mention that how do we know it is exactly? We found a consensus value that is achieves the minimum. That's absolutely right. Your question is right. The way we do this is by setting this alpha correctly. Whoever asked this question, it's a good question, because the question is, you're saying that basically we do some agreements in here, for instance. If I arrive at this slide. Yes, here, right? Because the question is, this is aiming for consensus agreement, and this one is doing some gradient flow. How do I know the location that we're going to agree on is going to exactly be that X star? How do we know this? The way we know this is by setting this alpha right. This learning rate will control if you do it, if you put it to going 0 too fast, it's not going to get to the right place. If you do it too slow, you have another issue. Okay, so it's tuning this is quite important. So that's the answer to your question. I don't know if I answered that question. If not, please write in the chat or speak up. For dynamic, does convergence to the average only happen for a strongly connected graph sequence? If the union of them, no, this is, so a sufficient condition is if the union of graphs in every b seconds, when you union them, it's a strongly connected, but that's only sufficient. It's not necessary. You can cook up a scenario where it's not strongly connected, but chance of life so happens that you arrive at that X star, but it is sufficient. And also there are much more technical sort of conditions that go way beyond this big connectedness. If you're interested, write me. There is something called infinite flow property that I've worked on. It's called infinite flow property. And this is a really, really, really relaxed situation where your graph could never actually be connected, but the weights on it, you know, they at the infinite limit, they're basically sending in enough information that things are going to work out. If convergence is impossible for unbalanced networks, why not rely more on balance? The problem is that in reality, sometimes we're given unbalanced networks, right? So the way to go about it is we cannot just exclude them. The way to go about them is we go and try to balance things ourselves. So the second portion of this push algorithm, what it's actually doing is trying to balance the network, right? It's keeping a measure. So if you look at this auxiliary part, it's keeping sort of track of how much imbalanceness there is, right? These numbers, as you can see, some of these numbers are going up and some of these numbers are going down. And the ones that are go up, for instance, could be measuring that you have more incoming than outgoing, right? And so by dividing through by these, we are sort of taking into account who has more influence. Because if you really sit down and think about this, the imbalanceness, the problem is the influence of some individuals is more than the others. So we want to cut that out. And the way we cut it out is by dividing through by the degrees, basically, right? Like that's the most kind of rough way I can explain this. Any other question? These are all very good questions. Yeah, I understand the topic might have been a little technical. I tried to kind of keep it as sort of basic as I could, but it's a mathematical topic, right? It's part of optimization theory, and so it's hard to talk about it without displaying some form of math. Oh, is it guaranteed to have minimum of fx or better approximate to the minimum of f if using averaging with gradient? I mean, most of these algorithms, they would guarantee that you go to the minimum of f. The function you actually arrive at is actually minimum of f. It's not going to be the minimum of basically it's not an approximate. You can actually guarantee conversions to the minimizer of f. I don't know if I answered the question, or I don't understand the question fully, but I hope I answered it right. Yes, go ahead.
Excuse me, Professor.
Yes, go ahead.
I just want to ask a question that I don't know if I understand correct. Is that required that the graph location should be the static and the connection can be the dynamic?
Yes, exactly. The connection is the dynamic part here. Yes.
But the connection can be regarded as communication, and
yes, absolutely.
The structure can be regarded as a distance, right?
Yes.
So is there any? I also heard a theory called the mean field theory.
Yes.
Yeah, I think the basic idea of this of the mean field theory is a little similar like what you have said.
Yes. So in mean field theory, right? The idea is exactly right. You react to the average of the population. But typically in mean field theory, we don't have like a graph structure, like the whole of population, we just average them and we use that value. Here, there is a structure, right, of who you take values of. But more importantly, is that mean field theory is about large number of individuals, in that you basically you make an assumption that the population is so large, right, that you can take all of them and replace them with like an average. Whereas here, for instance, in social networks, there's just too much structure to throw out. You know what I mean? Structure can influence things quite a bit, a specific convergence rate. And so that's why it's basically, it's a more refined version. There's something called graphons out there, which is the sort of the infinite limit of a graph. And so that would be the best sort of connection between the two. But it is similar to mean field, yeah.
Okay, so can you share more information about if the structure is dynamic and how to deal with that in such graph?
Yes, so you mean the structure of basically the communication graph, right? So what I showed here is that even if you have it, what you need to guarantee is that either in some window of time there is some connectedness, or you know, as I said, or basically the value of information at every edge, you can sort of integrate it through time, okay, and make sure that at least at infinite time, there's enough a squeeze of sort of information going from every two partition of graph. So you basically take the graph and you say, for every two partitions that I create of this graph, I need to make sure that the integral of the information going from, let's say, one partition to the other is sort of non-zero, you know, so that's the kind of tricks you use. It's technical. Unfortunately, I can refer you to references, but it's not something I can explain easily. But in terms of the nodes, you can also have dynamics in terms of nodes. For instance, what if we have a setting where there's arrival and departures? So there is a topic now called open multi-agent systems, and that's part of that discussion now. It's pretty recent stuff, but it is true that in many settings, the nodes are not even static. The new nodes arriving and some old nodes departing. So yeah.
It's kind of like ad hoc theming.
Yeah, similar.
Okay, thank you. Sorry, I have another question, maybe a basic question. Is that why we should care about the averaging value of your neighborhood or averaging your neighborhood graph?
Yes. So the only reason that we actually do care about it is because, remember, we want to find the minimizer of the sum, right?
Right.
And remember that the state is in the problem statement I started with, the state is a common state, meaning you see right here, I emphasize that this state is a common state, you know, in this slide. So the fact that it's common, right? This is the fact that it's common makes us think that if we exchange information with our neighbors, they have a different estimate, right? You see in this here, they have different estimates, right? So that's the idea. The idea is because there's a common value that's minimizing the sum, and we want to agree on it. We want to find. So this is one way of doing it. It's not necessarily the only way of doing it. There's quite other ways of going about this, but the most efficient one has been so far, at least, by using averaging. Because what would be the other way? The other would be to stack maybe all the states and at every time basically exchange that, but that's really communication heavy. It doesn't scale nicely with n. Whereas average is just one really tiny bit of information. The least amount of information really you can exchange, right?
Okay, right, got it. Thank you, Professor.
In a sense, yes, no problem. Any other question, guys? Okay, thank you everybody for attending the talk. I hope it was useful.